If this continues on from what I was talking about, the general theory, if Einstein's view of the cosmos were true, the cosmos, would be flying apart. There'd be nothing to hold it together. It would be like a bunch of spherical buoys and other buoys just randomly going all over the place, right? If Einstein's view of the cosmos were true, it would be flying apart, right? I think that's what the conclusion is here. Let's try this one for the last sort of basic idea. It's the elevator experiment, right? Is light bending? But before I do that, let me do a sort of simpler one. You can get these on YouTube. You can look under the Coriolis effect, and they have some experiments that went on. So here you have like a merry-go-round. You know, there's A and B for observers. They're sitting on a rail with seats apart from each other, whatever distance, and they're going in counterclockwise motion at a small speed. The ball, when they get into this setup here, the ball is sent across A towards B. And then what are they going to see? Well, if you're on the seats, A and B, what you'd see is the ball curve in the opposite direction. If it's coming, if the system is going around counterclockwise, you'd see the ball turn slightly clockwise, depending on the speeds and whatnot, right? If you're above it, if you're an observer in the seats, A and B, that's what you'd see. If you're an observer, let's say C above it, you would see the ball starting here, going straight across and hitting the target over here, right? The line of sight would go right with it. The ball isn't curving. It's just that it's an appearance. It's an appearance that it curves based on what the observer sees, what place he is, but it doesn't, in fact, actually curve. It goes straight. So, yeah, so that's just an apparent, right? And, yeah, so a lot of it has to do with the same idea of the elevator. But, again, it's an apparent, not a reality, the curve, right? And this supposedly says, you know, the elevator experiment, someone's in an elevator, they're accelerated up, and they see whatever light or whatever come in and bend to the observer in the elevator. If the elevator sees nothing else at just the elevator, then it can be that, right? Or it can show that it curves. Again, it curves to him, but in reality, it's not, right? What happens? So the light from the source over here, you know, will be straight. In other words, but if you have a line of sight over here, let's say a bullet instead of light. There's nothing holy about light anyway. A bullet would come through, line of sight, it would go straight. It would go straight. Even though the person inside might see it curve, right? In reality, it's just going straight. I can guarantee you that if I have a bell here, right, and you have somebody with a rifle over here shooting a bullet, and he can, you know, shoot through the elevator but not hit the person in the elevator, right? Regardless if the elevator is still, you know, not moving, stationary, moving at a constant slow velocity, or accelerating when the, you know, at a certain point when the person pulls the trigger on the rifle, it will hit the bell every time, because that's the line of sight. The rest, you know, is moving. You'd see holes, like, you know, one hole straight across, another hole slightly down because it's in motion, and then a bullet hole maybe further down because it was accelerating. But to the outside, in reality, right? Reality, not appearance. In reality, it went straight across and hit the bell every time. And this doesn't hold just for light. It holds for anything, right? Any object will appear to bend. You can have pebbles, you can have tennis balls or ping pong balls, you can have beer cans, you can have 57 Chevy. It doesn't matter. There's nothing holy about this situation here. It just shows that in this, it will tend to bend under acceleration. If this is just an appearance, right, and Mr. Einstein, the equivalence principle, if he based the idea that light bends because of this, he's wrong, right? It appears to bend. It doesn't bend. It appears to bend, right? And so what he's saying is, this through the equivalence principle is why light bends or deflects in a strong gravitational field. We don't need Albert Einstein to tell us that photons, light bends in a strong gravitational system, gravitational force. Newton knew that a long time ago, maybe others before that. So, the whole idea behind what I wanted to get across here is that there's a difference between appearance and reality. Appearance, as long as you understand it and you don't tie it to, make it seem like it's true, fine. But in reality, it's false. It's all false. Just like Mr. Einstein's idea that if you're traveling on at the speed of light, and another speed of light is shot at you at the mirror, it's going to bounce back. The question is, exactly how fast is that going to come back? I'd say it come back at the full rate. Because if you're just standing there with a mirror and it hits it and comes back, it should, within reason, be the same speed as when it comes out. And if you start to move, what you're saying is that two different situations would give you the exact same outcome, and that's usually not true, right? So if it's a speed of light going against a mirror, somebody flying at the speed of light, it comes back, it'll be twice the speed of light. The problem is, I don't know how we can test it. Because even if you have radar and you have the fastest plane or jet that we have now, the difference between the signal going out, hitting the jet and coming back, compared to the speed of the jet, is negligible. I mean, nothing. It's like a snail versus the quickest man in a 100-yard dash. The man will be down in the finish line before the snail even starts to cross the starting line. So you can think about it. You can think about it. Try breaking it down. Start with non-relativistic speeds, like 100 miles an hour or 1,000 miles an hour, and see what you come up with. So appearance versus reality, you have to watch for that. As far as I'm concerned, there's nothing true about this special theory of relativity. There's nothing true about the general theory of relativity. The only idea that I think Mr. Einstein had that works is for what he won a Nobel Award for, which was the photoelectric effect. So I think I'm pretty much going to end it there. Thank you for hanging out with me. Let me get to one last point. A gravitational field changes with position, whereas an acceleration can remain constant, right? I mean, if you go up in a gravitational field, the force is always changing. But you can rig a spacecraft or something to go at a constant acceleration. So, I mean, there is basic problems with the general theory, and it just isn't true, from Frank Draghi and all the rest. So, you can always get in touch with me. People will know how. Thanks for hanging on. I appreciate it. Thank you.